Astronomy Chapter 3, Orbits and Gravity. Now we are getting into more details, more specifics of the orbital dynamics, more physics. You'll see some mathematical equations. Today we will look into orbits based on the laws of Kepler. Johannes Kepler, 3 laws of motion. And next lecture period we will look into Newton's equations and see where does all the required force come from in order for all these moons and planets to be in the orbit as set by the Kepler. A chapter opening question, you will see this international space station in a different way at the end of the chapter, because you will have known the physics of it, the dynamics of it. This thing is not in a static state. This is not sitting up there in space. It is revolving around the Earth with orbital period. Every 93 minutes it goes around the Earth. Its speed 17,000 miles per hour. It's that speed, with that speed. Yet it does look like floating, because we see astronauts simply floating inside of the space station as if they are not moving. Why is that? We will see that. And moreover, we will be able to calculate its orbit, its distance, and its speed with the same equation provided by Kepler, which he found those equations based on the planetary motion of the planets around the sun, or motion of the moon around Earth, or motion of other moons around Jupiter and Saturn. You will see the resemblance, how one law, one physics equation can be applied to a different set. They all act in the same way. The physics of how the International Space Station revolves around Earth is same for, there are thousands of such artificial satellites revolving around Earth right now. The most popular ones are our GPS satellites. There are constantly 4, 5, 6 of them triangulating right now in your phone, because your phone is talking to that GPS signal. Okay. So these are, you will be able to see, how the International Space Station, or how it was planned, how it was calculated, its height, its speed, so that we know it will be stable at that point at the end of this lecture. And so Tycho Brahe, Johannes Kepler, and Isaac Newton, these 3 figures will focus on chapter 3. Their scientific contribution, it has more contribution than the previous one, because science is always building on the previous finding. One finds something like Tycho Brahe, Danish astronomer with good connections to the king, was able to build his own observatory back then in a place called Venn. And he built this observatory, Tycho Brahe, and he spent years and years observing the motion of the planets in the sky. And he would write all those astronomical data in a table. So it was all observing, writing their position and time on the table. And he had these pages, hundreds of thousands of pages of data collected from the observation of planets and stars. Yet, there was no real theory, or even there were some hypotheses, but no theory, no mathematical equations that would govern the motion of the planets around the stars. Whatever that data was there for, let's say, planet Mars, it was all for Mars. Okay. It was all pure observation. That became very handy. That came out very handy for his his fellow Johannes Kepler. So Tycho Brahe did all this observation for years, and he was Danish. He was in Denmark. Later part of his life, he moved to Prague, and that's where he met his student, Johannes Kepler, a German astronomer. Kepler, we'll call him Kepler. Kepler was very good in mathematics, and so he took all these observational data from Tycho Brahe, and he wanted to formulate a theory. Is there a pattern in the data? And based on that pattern, he wanted to formulate some equations. Later on, those equations will be called Kepler's laws. Actually, he formulated 3 laws, so they are also called Kepler's 3 laws. And again, here is his timeline: born in 1571-80, died 1630. Their discovery, the Tycho Brahe's observation, and how Johannes Kepler, deduced a mathematical relation of the motion of the planets around the sun, had a profound consequence on the modern science of planetary science, exoplanetary science. Currently, I'm doing research on exoplanetary science, exomoon. Every now and then I come back to solar system. I'm currently, like this week, I'm working on a project to find how many moons can stably orbit around the Earth. Right now we have alternate planetary Earth, and we only have one moon. There are so many other systems out there. I'm doing these theoretical and numerical simulations of systems where there is one sun-like star, one Earth-like planet, and I'm trying to find out how many moons of different size, the lunar size, the Ceres size, or the Pluto-sized moons can orbit the Earth. The work in progress will be soon sent to the Center for Publication Peer Review. I will let you know. But my point here is, even today, like yesterday, when I wanted to calculate the orbital period of my hypothetical moon, which can be closest to the Earth, I went back to Kepler's equations and worked on his equations to get those numbers. So that's what it means. It had a profound implication in the modern science. And so there are some of the definitions that you have to know for the rest of the semester, because we'll be using these terms a lot. Some are simple: circle, or let's just start with orbit. When you say orbit is the path of the sun or moon around its central body. And for moons, the central body would be their planet. For planets, their central body would be the sun. And for solar system, even our solar system is on orbit around the galaxy, the center of the galaxy, where there is a supermassive black hole. And so that path is the orbit. And that orbit have shapes, different shapes. Not quite circle, but we define a circle anyway. It's so obvious what is circle. It's round, yes. But most importantly, its distance to the circumference from that center is always same. That's the circle. And there is ellipse. Ellipse is an oval-shaped orbit. Okay, and so here is an example of an ellipse, and here are all the orbits of solar system. Of course, there are no such red, blue, and green lines in the solar system. These are imaginary lines. So the planets, more or less, they always follow that imaginary line. Based on their inclination and eccentricity of the orbit, they can fluctuate over time. More or less, they follow these paths here. And make a note: none of these orbits of the planets and solar system, the exoplanets, the millions, billions of exoplanets out there, or the path of our solar system around the black hole, none of them are circular. In reality, the orbit is always an ellipse. It's always elliptical, meaning when you flatten that circle, if you push from top and bottom or sideways, that circle gets a little flattened. That's what the ellipse is. The shape can be like this. It is kind of exaggerated here. And so some more definition before I continue. Semi-major axis. So this is example of ellipse. It's not circular. Okay. In this ellipse, center is the center point. You draw midline here, and this line this line is called the major axis, and the shorter one is called the minor axis. This is a longer one. Okay, the center is this center. Okay, and in any ellipse, there are 2 points, foci. This one and that one, singular focus. These are focus. And the brilliant finding of Johannes Kepler is that the orbit of planets around the sun is always in an ellipse. Ellipse is a geometrical shape which has 2 foci, and the sun or the central body is always at one of the focus, like this one here. This is quite exaggerated, meaning this orbit has large eccentricity. It is more flattened. Okay, it means this is our solar system here. They do look very circular. Yes, they have some eccentricity, meaning they have some flatness to that orbit, like this thing. And so, continuing definition, semi-major axis. So, major axis is the widest diameter of the ellipse. Minor axis is the other smaller diameter here. Semi-major axis is this distance from center to one edge here, or half of the semi-major axis. So this distance is called the semi-major axis. The eccentricity, other definition, eccentricity is E. So notation-wise, later in physics we will use a lot of symbols. Even some are carried to astronomy. So A, small letter A, means semi-major axis, always A. And small letter E is the eccentricity of the ellipse. What does that mean? So eccentricity, when I see that number, I can imagine how is that orbit? What is the shape of that orbit? Eccentricity is 0. If E equals to 0 means I have a perfect circle. Whenever eccentricity starts to go up, and it goes up 0 to 1, eccentricity can only have values between 0 and 1. If eccentricity is bigger than 1, means the orbit opens up. It's no more a closed orbit, it's a hyperbolic orbit. And when planets gets into hyperbolic orbit, meaning now their path is not closed, so they just go farther away from their central body. Now they are no more under gravitational influence of the star. And that can happen. We'll come to those situations later. And so basically, circle is an ellipse with 0 eccentricity. Equals to 1 means it's very flat, very eccentric. The flatness is very high. And the orbits with that high eccentricity are not stable. We'll discuss that later. And like 0.1, 0.01, 0.02, these are some of the eccentricity of the planets in the solar system. We'll look at those values in detail in later time. Okay, so what else I missed? So again, our solar system, the orbits of the planet are all ellipse or elliptical, with Sun at one of the foci. This is a little exaggerated, but circular, but it's not, Sun is not at the center. It's little left or right of that center. And so, and Kepler deduced all these by observing the motion of the Venus and Mars around the Sun. They would, observe their path, their position every day, and based on that, it was brilliance of Kepler to derive these conclusions. And this is true not just for solar system. Like I said, there are about 5,000 planets outside our solar system that have been discovered and verified as of today. They are in more than 1,000 stellar systems, meaning different star systems. And all of those planets obey Kepler laws. Well, 1 and 2, 1 is easy. Orbits of all the planets are ellipses, not circular. Okay. And the second one, the law of equal areas, that in equal interval of time, the areas swept out in space by a line joining planet and Sun are always equal. What that means is, this is our Sun. This is a little bit exaggerated version. So Sun is at one of the foci here, and the planet goes around in this orbital, in this elliptical orbit out here. And so if, let's say, the planet is at that point here, at point 3, in time t, it moves forward. And so if we draw a hypothetical line between Sun and the planet, this line here sweeps out an area shaded in this blue region. So it has certain area, a line joining 3 to Sun and 4 to Sun, and that area, and it takes time t, let's say 5 minutes. Okay, I can draw the area anywhere in this orbit, let's say when the planet is very close to the Sun, and so the planet is at point 1, and in 5 minutes, the planet has reached point 2, so I can draw area swept by the planet going from 1 to 2, and shade that region. The measurement of the area A and B is same. How can that be? Okay. We'll see later, but let me give you a hint. Speed. Okay. Whenever a planet is farther out from the sun, when it's far out from the sun, its travel time is 5 minutes. That 5 minutes has not changed, but its speed has slowed down. So its speed is very slow here. And when it comes closer to the sun, whenever objects are closer to the sun, its speed increases. And so in 5 minutes, it travels longer distance, because this perimeter from 1 to 2, this distance is longer than this. It's same 5 minutes time. So to cover longer distance, the object must speed up. And so again, that's the second law, the law of equal areas swept in equal time. When we do angular momentum, conservation of angular momentum, the product of the radius, mass, and velocity of an object is same when it goes from one state to the other state. That conservation of angular momentum dictates to have different speed at point A and point B. That may not make sense at all. We will look into Newton's laws, Isaac Newton's first law, second law, third law, and we will look into conservation of angular momentum, and that will explain further the difference in the velocity. But for now, please understand that the velocity, the speed of the object, when it's farther away from the sun, it's very slower, and whenever it comes closer towards the sun, its speed increases, and it zip fast, it goes around swift, and it slows down, goes all the way, very slow, and when it comes, its speed increases, and when it comes towards the sun, it flies out very fast. And that's one of the reasons. The Halley's comet, it takes what, 200 some years, because its orbit is so elliptic. It goes far out from the solar system, and its speed is very slow there, so it takes hundreds of years to turn around. But when it comes towards the sun, its speed increases dramatically, and it just moves by the sun at much faster speed. Kepler's first law, second law. These first law and second law, these two laws tells us the orbital shape, sizes, the velocity of the objects at different points in orbits, their speed at different points of the orbit. And the third law, another very important law, tells us about the relationship between the orbital period and the semi-major axis. What is orbital period? Orbital period, P, is time it takes for any planet to go around once, or for any moon to go around its planet once, or for any solar system to go around their parent central black hole once. Or you can run around the building, and time it takes for you to go around the building, that's the time period. Okay. And interestingly, there's a very good relation between the semi-major axis. Now you know what semi-major axis is. In the ellipse, distance from center to one of the points at the end. Okay. And he, based on the observational data made by him and Tycho Brahe, deduced that P square is equal to A cubed. So the square of orbital period is semi-major axis cubed. And now that has a very big consequence. If I know the semi-major axis, I can find how long will it take to go around. And here P, orbital period, is measured in years, Earth years, and A is measured in AU, astronomical unit. What is AU? Distance from Sun to Earth, that is 1 AU. Okay. And I say it's important because, for example, if I can find a distance to Venus from the Sun, where it's at, that tells me the semi-major axis of Venus. And by knowing that semi-major axis, I can tell its period, its time period. How long does it take to go around the Sun once? Just by knowing its semi-major axis. And this law applies to all objects that orbit the Sun, or all the moons that orbit the planets, or all other asteroids that orbit the Sun. The orbital elements. I'm sure we'll come to this topic again. Orbital elements. So once we have an orbit, the path of an object going around the central mass. I call central mass because that central mass can be Earth if we are talking about Moon. That central mass is Sun if we are talking about planets. So that orbit has orbital elements. For example, the semi-major axis is one orbital element. Semi-major axis tells you the size of that orbit. Bigger the semi-major axis, bigger the orbit, or farther away from the star. So semi-major axis tells us the size of the orbit. The eccentricity tells us the shape of the orbit, how flattened it is, from near circular to very flat. Take a circle, push it from top and bottom, it gets flattened. So eccentricity will tell me the shape of the orbit. Like, for example, Pluto has much flattened orbit compared to the other nearer orbits. Usually when the orbits are near to the central body or near to the star, they are more circular. And the third orbital parameter is inclination of the orbit. You see, these are almost aligned in the ecliptic, almost, they're not 0 degrees, but they are almost in the same plane compared to Pluto at quite an angle. This is the inclination of the Pluto's orbit with respect to the Sun's ecliptic. And there can be planets with 90-degree inclination. So there are planets in this plane here, and so the other planets can be orbiting at 90 degrees with respect to that solar plane. That's the inclination. And there are three other parameters: the mean anomaly, the ascending node, and the longitude of pericenter. These angles are quite complicated to view. I'll come back to them later because I need a good diagram to point it out. Okay. And so, based on these Kepler's third law, that equation, we can do some mathematics here. Imagine an object that is traveling around the sun. Some object, we know one thing about it. Its semi-major axis, 50 AU. What would be its period? Time period. Time taken for that object to go around the sun. So, because, like I said, remember Pluto takes almost 250 years to go around. It was only detected or discovered, 50, 70 years ago. So we haven't seen it to go around at once. We don't have that observational data. But based on how far it is, based on its semi-major axis, using Kepler's third law, we can theoretically calculate that exactly how long is the Pluto's orbital period. And we know this formula works because we have tested it for hundreds other astronomical bodies. So it's no more hypothesis, it's a law. That's it's Kepler's law. Whenever you say in physics, astronomy, when you hear law, that means it was originally a hypothesis, but those hypotheses have been tested again and again and again. They are now the law of nature. That's how the nature behaves. And so again, it's a simple math. You're calculating for period, right? P. So solve this equation. Square both sides. That square goes away. So P is the square root of A cubed. A is in AU. You can leave the units in AU because the period is in years and semi-major axis is in AU. We stick to that unit, and that's 50. So to that, and we know that object takes 353.6 years to go around the sun. And so here are the summaries.